We're continuing with our triple integral non-simple region instruction. This time we're having the triple integral given to us, and the plan is to basically make it change the order of the integration. So far we've done one example that involved spheres with non-simple regions, and then sphere, any example with spheres can come back, and most of them can be solved with another method easier. And so we want to go into more depth in this example rather than the one involving sphere. So when we start, when the integral is given to us like that, first thing to do is to figure out what each variable bounds are. So here z is sitting between 0 and 2 minus y. And then x is sitting between 0 and 4 minus y squared. And y is sitting between 0 and 2. That is, here z is sitting between z equal to 0 and z equal to 2 minus y. That is a plane z equal to 2 minus y. In here, x is sitting between the cylinder x equal to 4 minus y squared and x equal to 0. And then y is sitting in between 0 and between y equal to 0 and y equal to 2. So let's try to draw that picture. Thinking about this surface, z equal to 2 minus y, that is a plane that actually in zy, this is x, y, z, in zy zy plane, it looks like this. And this point is 0, 2, 0, 2, and 0. That point is 0, 0, and 2. And so it looks like that, and then the plane kind of sticks out. If you put a piece of paper perpendicular to that plane come out, that's the perpendicular to xy plane. There would be a plane that, or orthogonal to the xy plane, it would be the plane of z equal to 2 minus y. So that's one thing. And then I have the x equal to 4 minus y squared. So if I draw that in the xy plane, it's a parabola, and it looks like and so for let's say if x is equal to 0, then 4 minus y squared is equal to 0. So it looks like this, and it comes over here and ends up for x has to be 4. So it's 4, 0, 0 coordinate right here, and then it just continues that way. And then I know that this thing is not x and z are not correlated, and this plane is going this way, so the plane is cutting down this direction when with x and y. This should be a little bit more perpendicular, and then the plane is cutting. Oh, one thing, when I described 4 minus y squared, I just drew the trace of it on xy axis. Again, you can put a piece of paper and it would be perpendicular to the xy axis that goes around this, and it gives you a cylinder. And so then you connect the cylinder is getting cut by that plane on top, and it will look like something like that. So let's redraw it here, then like that. Here goes a little curvy, here comes back a little curvy as well. So here you can see that this is what we drew on GeoGebra, and this is the direction of X, and you can see that basically if I'm looking at it like this, I can see that X is basically bounded by this yellow surface and the plane Y and YZ basically. The other thing that I can see is that the projection on YZ plane is exactly a triangle. So setting up the integral in this order, meaning the most inner is in X direction, I look at this and it goes from here to here, meaning that the most inner is going to be from 0 to that piece of the cylinder, which is X equal to 4 minus y squared. 4 minus y squared. And then that would be f of x and y and z dx, the most inner. And then there would be two outer ones that I will need. And so let's decide about the outer ones. So the discussion that we had was that the outer ones are going to involve basically it will be y and z, and we saw that y and z looks like a triangle like this, and which the top is the basically, and we want the y to be the inside, so I want the inside to look like that, and then in direction of y, and that would bound y between 0 and 2 minus z, because the plane in here is z equal to 2y, and then bound z between 0 and 2, and so dy dz. Next is that, so this was another simple region. Next is we try to set up this as a non-simple region. Before moving on to setting up the integral into non-simple regions, I want to bring up one little detail in here. If you have noticed, the first thing that you choose is the most inner integral, and then after that the two outer ones, you figure out the projection over the plane that contains the two outer ones axis, and then it becomes literally, the two outer ones become a double integral on its own, and so that's how we actually work it out. So when does this integral is going to be in a non-simple region state? Look at the shape. If I turn it around in the y direction, there you go. So y direction, and the y is perpendicular to me, I can see that in y direction, one time I have the top part is going to be basically. So when I'm talking about this as a non-simple region, I can see that this part is the y equal to 2 minus z, and this part is x equal to 4 minus y squared, the positive part of that, which gives y is equal to square root of 4 minus x. And so I see that there are two basic regions in here, and this is the direction of the x, and that's the direction of z. So when I'm setting up the most inner integral, I will have two regions, region d1, and that's d1, which is running and has the cap as the blue part, and that runs from 0 to 2 minus z, and then f of x and y and z dy plus region 2 d2 for the outer double integral, and then f of x and y and z dy. And then there is a dA out here and dA out here. So the next part is that to figure out what is this projection and what is that projection, and how do we find them. It actually comes down to something a little different. So what is going to happen is that the outer integrals and to find this boundary over here, it's sort of, you see that there are the two regions together make a rectangle, right? And so what you want to do is to find this boundary, and to find that boundary you basically intersect the two surfaces that are meeting there, eliminate the variable that is not in the x and z region. So I'm going to eliminate that variable, and what do I get? I'm going to get 2 minus z is equal to square root of 4 minus x, and then if I solve this, I'm going to get x is equal to 4 minus 2 minus z to power 2. So that's basically, that's this curve. And so the region looks like that. This is x, this is z, and looks like that. And then I have two pieces. This piece that goes with the 2 minus z is going to go as actually here, that's d1, that one is d2. And then you get to set up the regions. Basically choose whichever you want to be the inner out of the two for d1 and d2, and then you solve. And I let you guys to complete this on your own. So we're ending this video by using two iClicker questions. iClicker question 15.3c, we write the integral as an equivalent iterated integral in the order dx, dz, and dy. So please pause and work it out, and then come back and listen to the solution. So I hope we really paused and we're continuing with the solution. So how does this work? What is explained in here is that z is running between 0 and y squared. Y runs between -1 and 0, and x is running between 0 and 1. And so you don't see in any of the inner ones that are functions of, actually any of the inner ones are functions of x basically. And any of the inner bounds are functions of x, and that says that basically you can graph these two bounds, the first 2 bounds 1 and 2, in the zy, and then that when you graph that one, and then it would be a cylinder over that basically. Then dx is just going to bound that cylinder, and that's how it works. And so if I graph this one, if I graph and z and then or y and then z, and I get it goes from 0 to y squared, so it's underneath y squared somewhere, and y runs from -1 to 0, so it's like that, a cylinder coming out of this page like that toward the z-axis, and it's cut into between the zy plane and the plane that is equal to that is x equal to 1. Now reordering this, again, if I'm starting with x as inner, I just said that this is a cylinder, field cylinder, cut with and then x basically at 0 and 1. So the bounds for x should not change at all. And so this is out, basically. And then we have the dz dy, and then dz dy bounds should not change neither, because the order is z is inside, y is outside again. So I'm looking at these, and I'll look at which one has that bound, and that would be A. We're ending the video with the iClicker question 15.3D. Rewrite the integral as an equivalent iterated integral in the order dy, dz, dx. And this is the same integral as the iClicker C. And so now the order is a little different from iClicker C. So please pause the video and work it out. Did you really pause the video? So I hope I did, and so we continue. And so how was the shape? We discussed that actually, if I look at the YZ plane, this shape is going to look like this little piece over here, and then -1, 1. It's basically 0, -1, and 0. That's the point. And then over here, which is 0, -0, -1, and 0. And then and toward the x direction, it's just gonna go, and it continues going over here, and it makes that shape. Now, looking at this, if I'm changing the order to go with y first, y runs from y equal to -1 to this kind of a curvy cylindrical shape. What is that curvy cylindrical shape? This is the negative part of this parabola, or this parabolic cylinder. Sorry, z equal to y squared right there. And that would be, when I solve for y, I get y equal to negative square root of z, because it's a negative side of the cylinder. And then so I have that, and I see that it starts from -1, goes to to that part. So what I have here and here are correct. Now I have to look at the outside too. The outside too, I see that if I look at basically the projection over XZ plane, I see a rectangle. And so that's not the answer. This is the answer.